Today I will talk about the coordination estimation in digital video coding. And here's outline. For introduction, I will talk about the video applications and why distributed video coding is important for this video application. Since distributed video coding is based on the distributed source coding, then I first quickly review what is distributed source coding and then talk about distributed video coding. For distributed video coding, there are mainly two key factors affecting the decoding performance. One is line information generation and coordination estimation. Here I only quickly review line information generation this way, since I mainly concentrate on the coordination estimation. And for the coordination estimation, I first talk about online coordination estimation, which proposed by the Brace in the 2008. This is paper, also my general exam reference paper. And then I will talk about our proposed on-the-fly coordination estimation, and finally draw the conclusions and future works. Digital videos have been applied to a lot of applications such as the broadcasting, video streaming, and digital videos need a large space for the storage and wide bandwidth for the transmission. So to maintain the video quality but reducing the transmission data rate, video compression technology provide important role. And for this one-to mining application case, the video will be encoded and the video will upload to the server, and many of the devices will download or watching the video from this server. And for this case, the video is encoded once, but it will be decoded millions of the times. So for this video coding application, the video codec need a multiple lightweight decoders, and encoders has a high compression performance. So now we look at the video codec about the video application. Give a video sequence. Suppose we want to compress the frame X, and we also suppose that we have adjacent frame Y. And now we only need to compress the difference between the frame X and frame Y and send to the decoder. But we want to have a high compression rate. We want to have a high compression performance, and that is need to minimize the difference between the frame X and the frame Y. And this goal can be done by performing the motion combination task. So from the corner figures, we can see that without performing the motion combination, the difference between frame X and frame Y is shown in this figure. The lighter pixel represents the large difference between the frame X and frame Y, and the darker point represents a small difference between the frame X and frame Y. So by performing the motion compensation between the frame X and frame Y, by performing the motion compensation, the difference between frame X and frame Y is shown in this figure. So we can say that the difference is smaller than the previous one without using motion compensation. So then the difference will be encoded and sent to the decoder. And here at the decoder side, we also assume that the decoded adjacent frame Y is available at decoder. So with this difference and the frame Y, we can easily recover the frames X with a very low computation complexity. And compared to the decoder, at the encoder, since it's performed the motion compensation, so the encoder has a large computation complexity than the decoder. So that is the video codec, which is satisfied to apply for above video applications. And now we have the new video coding applications, such as wireless video surveillance, multimedia sensor network, and wireless PC cameras or mobile camera phones. So for this -2-1 case, all of the devices want to send videos to the server, and also these devices has a limited computation complexity or constrained by the lower battery. So for this case, the video codec need multiple light encoders, and also due to the limited bandwidth, the encoders not only to have the lower computation complexity but also have the high compression performance. So the traditional video codec we just talked about cannot apply to these video coding applications because the traditional video coding has a very large computation complexity at the encoder side. So we need a new video codec to apply for these video applications. The distributed video coding today I will talk about it actually fits well this scenario because the distributed video coding shifted the computation complexity from the encoder side to the decoder side. And the distributed video coding actually is based on the distributed source coding. So here I quickly review what is the distributed source coding. Distributed source coding is the compression technology to comprise two or more physically separate sources. And by performing the joint decoding of these sources, and all the sources will be recovered. Here, the distributed source coding also states that given the joint decoding, the separate encoding can achieve the same performance can achieve the same performance of the joint encoding. Distributed source coding can be divided in two cases. For the lossless case, it's usually called slip-and-wolf coding, and for lossy case, is called Wyner-Ziv coding. For the asymmetric slip-and-wolf coding, only source X is considered to be encoded and sent to the decoder, and source Y is considered as the decoder treated as side information. So by performing the joint decoding of the source X and source Y, finally the source X will be recovered. Here at the encoder part, the source X does not need any additional information for the encoding. Actually, the most of the channel codings used here for the encoding, such as the source X just contains a parity check matrix and to generate the syndromes, and the syndromes will be sent to the decoder to help for decoding the source X. And for the lossy case Wyner-Ziv coding, the continuous source it just contact and follow the slip-and-wolf coding. So yeah, for the Wyner-Ziv coding and slip-and-wolf coding, the only difference is that it introduced a quantether and dequantether before the encoder part and decoder part. Distributed video coding is a new paradigm based on the distributed source coding principles. And a particular case of the distributed video coding is called Wyner-Ziv video coding, which is based on the Wyner-Ziv coding. So similar to the previous procedure, the source X and Y will be replaced by the frame X and the side information frame Y. And here we have another option that is the transform and the transform module. So if we didn't take into account the transform and the transform module, and this procedure is called the pixel domain distributed video coding scheme. And otherwise, if we take into account the transform and the transform module, and this case is called the transform domain distributed video coding. For the transform domain distributed video coding, actually it transformed these pixels in the frame to another domain, and only keep the important information in that domain and discard the not important information. So the transform domain the transform domain DVC has a better performance than the pixel domain DVC, but it has a lower, it has a little higher computation complexity. In a general way, the overall procedure of the pixel domain DVC is similar to that of the transform domain DVC. So in the following presentations, I only concentrate on the pixel domain DVC. Then we talk about the practical implementations of the Wyner-Ziv video coding. And given the video sequences, we first divide the video sequence into the keyframes and the Wyner-Ziv frames. And for example, here we denote the old number terms, the old number frames at the keyframes, and the even number terms at the Wyner-Ziv frames. Then the Wyner-Ziv frames will contact and then encoded through the slip-and-wolf encoder, and then the generated syndromes will send to the decoder. For the keyframes, it will encoded by the traditional frame coding such as 8.264, and then decoded independently as a decoder And these decoded keyframes we use to generate the sign information frames. Then, by performing the joint decoding of the sign information and the received syndromes, and finally, and then perform the dequantizer, then we can recover the frame X. And here at the decoder part, there are two key factors affecting the decoding performance. One is the interpolation module, which is used to generate the sign information frames, and the other module is the correlation estimation module. Since actually the sign information frame is initial estimate of the Wyner-Ziv frame. So if the sign information has a better quality through the interpolation technology, it means that the decoder needs a fewer syndromes sent from the encoder part. And given a generated sign information frames, the difference between the original Wyner-Ziv frames and sign information frames will be estimated. If the correlation noise between the Wyner-Ziv frames and sign information frames is estimated well, then it means that the decoding performances will be getting better. So that two part is the challenges in the distributed video coding. So in the following, I first quickly review the sign information generation, and then mainly focus on the correlation estimation. And for the sign information generation, this sign information generation since the sign information generation plays an important role in the distributed video coding, so there's a lot of research work in the literature. Then here I only talk about the commonly used motion completed interpolation technology. The frame interpolation means that we're only using the existing adjacent frames to generate the intermediate frames. So for example, here we only use the T-1 or T+1 keyframes to generate intermediate frames, which has the sign information of the Wyner-Ziv frames. And the validation of the frame interpolation is based on the assumption that the adjacent frames are similar, and the changes are only introduced by the object motion or the camera motion. So we want to estimate the motion between these adjacent frames and then interpolate the intermediate frames. How to estimate the motion between two adjacent frames? Here I also to talk about the commonly used block-based forward motion estimation. And here the T frames is also referred to as the backward frames, and the T+1 frames is also called the forward frames. Then given the block in the backward frames, we want to find the best match block in the forward frames. And here the right region represents the search region. We actually enumerate all the candidate blocks in the search region to find the best match block. The best match block actually has the minimum of the mean absolute difference between the corresponding pixels. Here suppose the best match block of this current block is this block, the blue one. And now the distance between the candidate center of the current block and the best match block is called motion vector. So here is the right arrow. Since we want to interpolate the frames between the backward frame and forward frames, so we should take a weighted sum of these two frames. So here we plus the backward block xb and plus the forward block xf and divided by 2. And in addition, the motion vector is between the backward frames and forward frames. So we also need to divide this motion vector so we also need to divide the motion vector by 2. So here for the forward frames, we take the plus sign. For the backward frames, we take the minus sign. So by sum the motion compensated backward block and the motion compensated forward block, and divided by 2, and we can calculate the interpret block in the interpret frames. So by following these procedures, we can get the interpolated frames. So that is the sign information generation technology.
What is the V?
V is the motion vector. Actually, Vi represents the motion vector from the horizontal part, and the Vj represents the vertical part.
Okay, why did you divide it by 2?
Yeah, actually here it based on the assumption that the interpreted frame is equidistant with the backward frame and the forward frames. So yeah, the assumption is that the motion vector from backward frame and forward frames, yeah, the intermediate frames have the same distance with backward forward. So the motion vector divided by 2. Yeah. So now we'll talk about the correlation estimation. First, we will look at the correlation model using in the Wyner-Ziv video coding. Most DBT designs so far usually model the correlation model as a Laplacian distribution. So here alpha is called Laplacian parameter, and the sigma square represents variance of the residue frame between WZ and side information frames. Since we want to estimate the correlation, now we just use to estimate the correlation parameters alpha. And since the high motions between the video frames and sometimes the illuminance changes in the frames, so the alpha varies temporally and spatially. Now we'll talk about the online correlation estimation technique. This online correlation estimation scheme actually using the 3 granularity levels to estimate the correlation parameters. The first level is called frame level, and then the block level, a pixel level. The frame level, it means that each frame is characterized by the same correlation parameter alpha, and block level means that each block have the same correlation parameter, and each pixel level means that each pixel have the different correlation parameters. Now we look at the frame level. For the frame level, since it's the online correlation estimation technique, the original Wyner-Ziv frames cannot be available at the decoder side. So we cannot calculate the residue frame based on the original frames and information frames. So now we need to approximate the residue frames. The residue frames approximated by using the motion compensated forward frames and the motion compensated backward frames. So we minus this. We're using the motion compensated forward frames minus the motion compensated backward frames and divided by 2, and it takes this formula at the residue frames. Then we, based on the variance definition equation, we can calculate the variance of these residue frames. And here the H and W represents the height and width of each frames. And here, based on the correlation relationship between the Laplacian parameter and the variance, we can get the Laplacian parameter is equal to this equation. This is about the frame level online correlation estimation. Then we look at the block level. Okay, I think that I should not call that part. didn't follow.
No, what is
Yeah, I
it?
changed the slides, but the delay is so long.
Okay, I guess it's just too slow, isn't it?
Yes, it's too slow.
This is whole image or even that is something that's
This is a home image. Because that reason.
I have no idea. Stop and try again. Stop it.
Is this one?
I haven't stopped, but I don't know, that's because they stop, it would be split into two.
Oh, yeah.
It's kind of annoying. This is- In the audience, we are now having technical difficulty.
This is good.
In the audience, in the YouTube.
Sorry, audience.
Languages. Oh, okay, okay.
Thank you. Then we look at the block level. The block level also refers to calculate the residue frame keys block generation. Sorry, first calculate the residue frames keys block, and here we're also using the interpolated forward keys block and interpolated backward keys block to generate the residue frame keys block, and then also using the variance definition, we can calculate is the variance on the keys block. And then here, the correlation parameter alpha computation, it has two cases. For if the variance of the keys block is smaller than the variance of the residue frame R, it means that this interpreted block has high quality than that average on the residue frames. So to maintain the uncertainty between the Wyner-Ziv frames and sign information frames, this correlation parameter at this time is bounded by the value alpha R, which is calculated in the residue frame level. And if the variance of the residue frame keys level keys block is larger than the variance in the residue frames, it means that this interpolated block has a lower quality than that averaged on the frame residue frame level. So at this time, it's corresponding to have a lower confidence about the similarity between the Wyner-Ziv frame and sign information frames. So we should choose, so it will choose a smaller correlation parameter alpha. Then for the pixel level, the variance of the pixel is now equal to the each pixel in the residue frame, the square of each pixel in the residue frames. And here,
You didn't close the parenthesis.
what?
I think you didn't close the parenthesis.
Oh,
Bracket.
yeah.
It's
Yeah.
a bracket?
Bracket, yeah. Then here for the correlation parameter alpha, I divided it into 4 cases. Also for the first case, it's similar with the previous one. It means that this block, the interpreted block is very close to the original block in the Wyner-Ziv frames. So here, we using the variance calculated on the residual frame as a bound. So at this time, all of pixels in the case block will take the correlation parameters equal to this value. And for the second case, case here it consider another measure. It's called variance distance. It's called the distance. Actually, it's equal to the average value of the R frame case block minus the average value of R frames. So it's kind of to describe how far the case block from the whole frames. So for this part, it means that the interpolated block has a lower quality than that one average on the residual frames. But this part means that the block, even it has a lower quality, but the interpolated block is still very smooth or very very smooth or very sorry, I should to I should talk about this again. I will talk about this. And for the second case, it means that the interpolated block has a low quality than the one average on the frame level. But this part means that the distance of the average value of the R frame case block is very small. So it means that the interpolated block, it is still interpreted well to the original block in the Wyner-Ziv frames, but it has a lower confidence information than the first case. And for the third case, the variance of the case block larger than the variance of the residual frames, and also the distance larger than the variance of the residual frames, but the pixel is interpreted very well because it's smaller than the variance in the case block. So at this times, the pixels will take the confidence level that is equal to that one in the block level. And for the last case, it means that each pixel doesn't interpret it well. So at this time, it provides a lower confidence information, and so it should choose the lowest correlation parameter based on the definition, the relationship between the correlation parameter and the variance. So this is the online correlation estimation, and then this online correlation estimation model was tested on this video sequences. Since in the pixel level, actually, it has a deeper adaptation for the changing statistic between the Wyner-Ziv frame and standard information frames. So from this result, it showed that the finer granularity levels and the better decoding performance for the rate difference columns here. Actually, it is the difference between the corresponding granularity and the rate in the frame level. So here we can see that the pixel level has a rate decrease. We can see that the pixel level has a large rate decrease than the one in the block level. And here, the similar phenomenon also shows in the offline. Here I need to mention what is offline correlation estimation. Offline correlation estimation using the similar rule with the online correlation estimation. The only difference is that it uses the original 1 and 0 frames to calculate the residual frames. Here, the performance of the offline correlation estimation is just used to treat it as a benchmark performance. Hence, in the practical applications, the original 1 and 0 frames cannot be available at the decoder side. And however, for the online correlation estimation technique, they have some disadvantages. The first one is they just use heuristic rules to estimate the correlation parameters before the 1 and 0 decodings. And it does not take into account the received encoded syndromes into the correlation estimation. And we know that the received encoded syndromes actually come from the original 1 and 0 frames. It includes important information of the 1 and 0 frames. So,
excuse me, what's
right.
the received encoded syndromes? What's the meaning of that?
Yeah. Yeah, here. Actually, the online correlation estimation based on this workflow, and here they're only using the interpolated they're using the motion compensated frame, backward frames and forward frames to define the correlation parameter. Here, right? But here we have at the encoder side, it will send some encoded syndromes to the decoder side. And these syndromes include the information of the WZ frames, right? But as the correlation estimation part, it does not take into account this information. So if we take into account this information, it will improve the correlation performance. So this is I will talk about our proposed work on the fly correlation estimation. So in our proposed work, we take into account the syndromes to the correlation estimation to improve the accuracy of the correlation parameters. And the syndromes are also used for the 1-0 decoding, and we want to take into account the syndromes in the correlation estimation. We will define a module which can perform the 1-0 coding and correlation estimation simultaneously. And actually, our design model is based on the factor graph. So before I talk about other model, we quickly review what is factor graph. Factor graph represents factorations of the function. So if the factor function f x, y, z is factorized into the 3 factors, and the x, y, z represent the variables, and we have the 3 factors f a, f b, then the factor graph of this factorization of this function can be represented in this figure. And belief propagation algorithm as a message passing algorithm can be performed on the factor graph to calculate its marginal probabilities of each variable node. And the belief propagation algorithm actually have the several steps. For the first step, we will update the variable node. So it means that the message sent from the variable node I to the fact node is equal to all the incoming messages except the one sent to the fact node A. And then we will update the factor node. it means to the fact node A will send message to the web node, which is equal to the product of all the incoming messages and times a factor function fa. And then we will iteratively performing these two steps until it will convert. We can calculate the belief of this variable node. The belief is equal to the product of all the incoming messages. Then we can make decisions. If the belief of xi equal to 1 is larger than the belief xi equal to 0, then we think about that the xi equal. Then we take that the xi approximately equal to 1. Then based on the factor graph, then we can define our design model. And by representing joint probability distributions of the sign information and the 1 and 0 frames, here we use X to represent, and the received syndromes, we define this factor graph in region 2. Actually, this factor graph is a traditional joint, it's a joint 1 and 0 coding model. And since we mentioned that we want to combine the correlation parameter estimation and the 1 and 0 coding together, so we introduce some correlation parameters, sigma 1 and 2, sigma n primes. And here we let each variable node to connect several of the sign informations. It means that this several it means that the several pixels in the sign information frames will share the same correlation parameter. And here, this will assume that correlation is very temporary and spatially very slow. And so make sure that we introduce the factor function h1, 2, or the factor function in region 1 to make sure that the values of the correlation parameters make sure that the values are not have the large difference. Then this is our design the factor graph for performing the 1-0 coding and the correlation parameter. Based on the factor graph, we can using the message passing algorithms such as propagation algorithms to finally decode the 1-0 frames and the correlation parameter. And here, since we know that the correlation parameter is varies in time and space, so it typically is continuous variable. And since propagation algorithms only can work on the discrete variables in a small alphabet size, so we cannot perform the propagation algorithm on this part directly. So in the Bayesian theorems, if we want to estimate the correlation parameters, it corresponding to the calculation posterior distributions of this parameter. And since now we cannot use the propagation algorithm, we will use approximate method to approximate the posterior distribution. Now we first consider the stochastic approximation method and the particle filter algorithm. So actually the intuitive ideas mean that at this part the message passing will send the probabilities of this node equal to 1 or 0. But at this part, the message passing algorithms will have several labels. Suppose we sample the n number of the particles for each variable node. It means that this message will have the 10 labels, and each labels will have the value to represent the candidate value of this correlation parameter. Then this correlation the values of the correlation parameters, it will be updated according to the particle filtering rules. And here we will quickly review the particle filtering steps. First, we have the suppose the NP 10 number of the particles, and initially the particle weight is obtained from the belief generated from the last belief propagation algorithms. Then we will discard the particles with small weight and only keep the particles with the small weight. And then we will resampling keep the particles in order to make sure that the diversities of the particles, we will take the random works on these particles. Then we will continue this step until it converges. Then the particle algorithm will approximate the posterior distribution probabilities. Sorry. And that is a big picture of the proposed Dr. John Bittlett decoding modules. Now we'll show that conclusions. Here we consider the time-varying correlation models, and we take into account the received syndromes of correlation estimation. And here we design a model for performing the Wyner-Ziv coding correlation estimating simultaneously. And we propose a particle-based propagation algorithm correlation estimation. And here, since the particle filtering algorithm has a large computation complexity, so in the future works, we will consider the following task. Here, the deterministic approximation methods such as the expectation propagation algorithm can have the achieve the comparable performance with the particle filtering algorithm, but it had a very low computation complexity. So in the future works, we will try to perform the expectation propagation algorithm for the correlation parameter. And then we will compare the performance of the particle filter method and the EP algorithms. And then we will maybe consider to implement the both spatial and the temporal correlation estimation in distributed multivariate video coding. Okay, that's it. Next question. Thank you.